Welcome to a special Advanced Manufacturing Media webinar. Our presentation today is Implementation of Metal Additive Technology on the Factory Floor. We will hear from Francisco Medina, Senior Specialist in Materials Development at Arcam. He's currently stationed at Oak Ridge National Labs, where he manages Arcam's R&D activities in North America. Hello, I'm Bill Koenig, Senior Editor at Manufacturing Engineering, published by SME. I write about additive manufacturing for the magazine and its website, advancedmanufacturing.org. I'm your host for this webinar. Our sponsors today are Protolabs, Renishaw, Stratasys Direct Manufacturing, and SLM Solutions. Metals 3D printing has grown significantly in the past decade. Additive has gained momentum in aerospace and medical manufacturing because of its ability to produce parts with intricate, complex shapes. Metal additive processes such as Electron Beam Melting and Selective Laser Melting are powder bed fusion technologies that use alloyed powder and a focused energy source to melt and build components layer by layer. Francisco Medina, our presenter, is knowledgeable on the subject. He received a bachelor's in mechanical engineering in 2000, master's in 2005, and a doctorate in materials science in 2013, all from the University of Texas in El Paso. He has been involved in additive manufacturing for 15 years. We're pleased to have him join us for this webinar, and manufacturing engineering coverage of additive manufacturing or 3D printing is very important to us. Earlier this year, we published a special additive manufacturing section. You will be able to ask Francisco questions after his presentation using the Q&A box that will appear on the right of the screen. Time permitting, these will be answered following the presentation. Time runs out before we can get to all the questions. We will make sure the answers are emailed to you. With that, I pass the presentation over to Francisco.
Yes, hi. How are you doing? Today, I'm going to be talking about implementation of metal additive manufacturing technology on the factory floor. Correct, and okay. So first, about additive manufacturing, how it's been gaining a lot of momentum. Currently, new world report stated, that additive manufacturing market is worth $4.1 million in 2014, and now we're getting new statistics that is worth by 2020 it'll be worth over $17 billion. So that's very, very impressive. And now many companies are going into production with metals AM, and it's not just for prototyping anymore. So that's very, very exciting. Yes, so now today, as you know, GE Aviation has made great leaps in additive manufacturing of metals. They're going into production with their fuel nozzle, and just recently, they went into production with a engine sensor, which provides pressure and temperature measurements for the engine control system. As you could see here, in February, they began retrofitting this upgrade with a T25 sensor and their EG90-94B engines. So that was very impressive. Also in aerospace, Pratt & Whitney, they already started going into production with electron beam melting and laser powder bed fusion, with their new PowerPure PW1500G engines. And this Bombardier this year, so that's also very impressive, and they already test flew and also have delivered some planes with that. Also, another more aerospace news, Rolls-Royce today, they have built and designed the biggest additive manufacturing part. As you can see here, these are 1.5 meter diameter bearing houses inside the Rolls-Royce Tread XWB97. So as you could see, these were actually built in the Arcam Q20 system. You can build up to 4 of them at a time, and then they're welded together and set in the engine, and they have already flown, so that's also very impressive. If you go into more production, in aerospace, GE Avio today, they're testing and they plan to go into production by 2017 by using turbine blades. As you can see, these are made out of Thai alumina, and you can actually build these pretty fast with EBM technology. You can pretty much build around 7 hours a blade. So you can, and then they're doing testing and they're currently flying these. And like I said before, they'll try and go into production by 2017. So if you start looking at the numbers of all the systems that have been sold, it's getting pretty impressive. By 2013, over 350 systems were sold, and this includes all the additive manufacturing and metals. Last year, 2014, there was over 650 sold, and this year is going to increase too. So that's very impressive. And by 2018, as you could see, this is information that I got by Juan Trump, and it says that's going to be over 4,000. I don't know how true that is, but it still shows very impressive data. If you look at other markets that are exploding, it's not just aviation. Medical implants is going very strong. Currently, over 50,000 medical devices have been implanted, worldwide, and probably more. And then also space and satellite is going pretty strong. As you see, there's a lot of companies going into production with this. And other areas, like defense, Air Force, Army, UAVs are becoming huge. A lot of these are going to be, are actually now being printed, and also a lot of new materials are being developed. One of the big advantages of EBM or about additive manufacturing in general is that now you start looking at other materials, that are not they're not easily made by traditional methods. A great example is Thai alumina. With Thai alumina, casting is very hard. You get a lot of cracking. But with additive manufacturing, some of these wonderful materials that have a lot of great benefits that it cannot be manufactured traditionally can be made very nice with this technology. So today I'm pretty much going to be focusing on powder bed fusion of metals. As you know, there's other metal systems out there like direct energy, but I'm just going to be focusing on these, right? And powder bed fusion of metals, as you know, is an additive manufacturing process within a thermal selective fused region of a powder bed, right? And these are pretty much broken up into 2 different areas. One of them is electron beam, which RCAM is the only company that chose this. And the other one is laser-based process, which there are several manufacturers, EOS, Concept Laser, 3D Systems, where they purchased the Phoenix system, Renishaw, and also SLM Solutions. So first, with the electron beam process, I'll go over the way that it works. It uses electron beam that is 3,000 watt system. The beam melts each layer by layer. It usually is done around 50 micron layer thicknesses. Depending on the material, you can go up to 200 layers. You have enough energy in the gun. The system moves extremely fast. And then also, what's nice about this technology is that it's inside a vacuum system. So you get a lot excellent material properties, and you don't get contamination. Something else also to look at for the system is that the powder distribution that it uses is around 45 to 105 microns. And we do this for certain reasons. And then also something that's nice about the system is it's a high build temperature. So we actually preheat and post-heat the bed, and we maintain it. We keep it hot. So for like Thai alumina, we keep the bed temperature around 1080 Celsius. For titanium, around 600, 650. Right? And also something that's nice about doing this is that, you don't get any internal stresses. You don't have to do some stress relieving. here, as you can see here, we have a technology that's called multi-beam, and by doing this, we can actually have several different beams that actually work together. Or it's just one beam, but several melt pools going in at once. And here we're doing supports, and then at the end, we take a picture, which didn't come out. So now, when we look at selective laser melting, as you were aware of that, we have Brenneshaw, like I said, EOS, concept laser, selective laser melting technologies. And the way that the system works is the metal paddle bed fusion. It originated with a 100-watt laser. That was a long time ago. But now the new systems, they can go up to 1,000 watts. Some of them have two 2,000-watt lasers. So they're getting faster. The majority of the systems are operated in room temperature and pressure, and it's maintained with nitrogen or argon environment. The technology also scans pretty fast at 20 meters per second. In variable focus diameters, as you can see, so it's a smaller, larger beam. With this, the powder, because of the layer thickness that they do, because they do 200 microns or 20,000 to 100 micron, they use powder diameter, smaller powder diameter. Some technologies use 0 to 25. It varies depending on the technology and the layer thickness, and also in the material. But they usually vary on from 0 to 45 micron diameter. Here is the selective laser melting process, as you see. So the first thing that you have to focus on before you try to purchase some of these systems or get in the business of additive manufacturing metals, you have to have a good focus. A lot of companies, you can focus on research, prototyping, or production. There's a lot of issues. A lot of companies have start off doing research, doing SBIRs, STTRs. They've been very successful. Doing material development for the United States Army, Air Force, Navy, DARPA, also Department of Energy. There's a lot of research money over there funded for smaller companies or just companies in general, so they can do production or research in additive manufacturing. When you start going into prototyping, you still do a lot of prototyping for different companies. NASA is one of them that they've been using a lot of different companies to do nozzles. Aerospace, as you could see, or defense, right? And then also, if you're going to production, a lot of the big guys, Boeing and GE, Airbus, also Lockheed Martin, also they're starting to go into production with additive manufacturing. So these are those OEMs, that, and also tier 1 suppliers like JKN that are actually need people or companies. It looks very, so it's a good way to start getting funding. First, when you start getting a system, you have to look at what's going on. So you have to get real expectations. There's a steep learning curve. That takes from 6 to 8 months, and actually to really know about the technology. Initially you will not obtain good parts, or what I'm calling here semi-perfection. It takes a lot of skill. As you could see, there's a lot of stuff that can go wrong with the build that you have to know the correct setup. Machine software, there's a lot of software. Each company has their own software that they use, to be able to process these STL files and set up the support. And also part setup is very, very important. Orientation and support is kind of the key to get a really good, successful build, as you could see, especially when it comes to, as you could see, some of the parts that I have here, especially one on the side, is that you can really pack up some of these machines, to get really good throughput on them. As you can see, if you start packing them, they start becoming like, if you're familiar with Selective Laser Centering, that you can actually start packing parts up. But doing this takes a lot of skill, and you have to be able to know exactly what you're doing, and that will take some time. Well, first, when you start looking at these systems, you have to think about, safety first. You have to be able to read the material safety data sheets, that is provided. You have to, something that's very important about this is you're dealing with really fine powder, especially like we're getting to the 0 to 45 range. You have, depending on the material, it can be an explosion hazard, and I'll go into more detail on that. You also can get slip hazard, if you lay material on the floor. Respiratory hazards, as you see with this, if you have a new system, and then it, and after just 2 weeks, it becomes pretty dark. You can get skin irritation, or you need eye protection. And then also there's a lot of machine hazards. There's a lot of moving parts in these systems, internal systems. So you have to be able to be careful with that. And some systems, I know EBM now they're starting to implement light curtains to make it more safe for people. When you start looking at powders, like I said, something that we do really at RCAM that's been pretty good is we do a lot of RCAM. We do powder our explosives, like I said before. So we have to do a lot of independent testing by other institutes. So we do what's called minimum ignition and energy, and this is done in a dust cloud. So we try and by following these standards, as you see here, we really try to figure out what powder is safe to be used in our machine. So in order for us to use for the user to use a powder in our system, we have to prove to us that it's safe. So we do it by doing this kind of testing. And when we do this, you'll be, as you could see, this is a fire and explosion minimum ignition test that shows, depending on the powder particle size, that proves a very important part. When you look with tie alumina, if you look on the side, or if you look at, let's start from the right side, left side going to the right, you start out with 45 to 105 RCAM Tie 64 powder. And for our machines, we need a minimum of 30 millijoules, minimum ignition allowed. That's what we decide. If we go to 25 to 45, if we go below, as you can see, it a little bit dips below that, so that's why we stick to 45 to 105. If we go with Tie 64 from 0 to 45, as you can see, it's very, very hazardous, and we don't really allow that in our systems. When we go with Tie Grade 2, as you can see, 45 to 105, same thing, it's pretty safe. And then, when we go to 45 to 105, grade still within our usable limit, which is 30 millijoules. So next, what I want to show is a presentation on combustible metals used in 3D system printers. This was presented by Bob Solosh in the National Fire Protection Association in Albuquerque, New Mexico. So what happened here is, as you know, I'm located at Oak Ridge National Labs at the manufacturing demonstration facility, and something that we really try and focus here is on the safety. And so they give us a lot of training on different powders, how to handle them, you know, what can be safe, and then this is one of the presentations they showed us. So there was a powder department. It was an explosion in 2003. Powder Part is a small new contract 3D printer company, and they had an issue. What happened there? They were using Ruvac 935 wet port vacuum cleaner, you know, and what happened is a young engineer had just completed his training, his first parts, and he had not received adequate training on how to use the wet vac. After removing the workpiece from he was using Ruvac without attaching any ground, bonding wire, or even checking the water level. So that was pretty bad. So if he was trained correctly and he was using this technology property, you know, this probably would not have happened. I'm trying to go to the next slide. Okay. Yeah, and then as you see here, an explosion occurred in the vacuum, and this produced a flash fire in the surrounding area. The engineer was severely burned and injured. Responding personnel had difficulties extinguishing the fire because one of the reasons they were not up to code, they did not have a Class D portable extinguisher, that's also very important when you're dealing with this technology. And as you can see, there's some of the picture of the portable vacuum after explosion. Also, the machine that they were using also suffered some damage. And that's a pretty heavy vacuum cleaner, and it just went off the roof. And you can see the hose also kind of damaged. So what happened here, you know, was it could have been preventive. You know, OSHA gave some citation issues, you know, for combustible dust and fire explosion, hazard from metal alloy powder. You know, one of the first citations that they gave was because it was not electrostatically discharged, though they didn't have enough correct grounding. And also, they also gave them some issues because they did not have no argon monitoring was used. Another one was no fire-resistant protective equipment was worn by the person operating the machine. No hazard assessment, and then also no training to personal protection equipment for the poor guy that got hurt. And one of the biggest one also was no Class D metal fire extinguisher, which is also very, very important. When you're looking at this technology or these fine powders, you know, you always have to have that, because if you do water or something else, it just makes it worse. So OSHA November report, the fire explosion hazard 3D printed with combustible powders, you know. This brought up a red light pretty much all over the United States. Not clear yet if the report was going to be released to the public. But something that came up, you know, they started with the committee, or the National Fire Protection Association. They started draft a section for 3D printers, so that was pretty good. And the people that are actually leading this are here at Oak Ridge National Labs. In the general chapter, aluminum or titanium, you know, required certification for use of combustible metals. You know, something else that was nice about this, and that we're actually implementing it very heavily here at Oak Ridge, which is nice. They're expanding the sections of portable vacuum required interlocked for grounding, connection, and minimum water levels. So that's what we're doing. And also draft new paragraphs of training for printers and for portable dust collectors. So there's a lot of stuff that is being done here. So now you see a little bit of the dark side. You know, there's also some other stuff that you have to look at, especially when you're going to be investing in this equipment. The machine costs, you know, machines range from $650,000 to $2 million, so that's a hefty change. Material costs are also depending on the material that you're using. As you know, there's a lot of different materials that you can print. It's expensive. You know, I've purchased powder that's $60 a kilogram, all the way to purchasing niobium powder for research that was over $1,000 a kilogram. You know, so it's pretty expensive depending on what you're using it for and what you're building. You know, powder quality is very important. You know, I'll go into a little bit more on that. Finer particles are more expensive, you know, because it's harder to build smaller spherical powders and bigger powder, especially depending on the different ways that the powder is manufactured. Something else that you have to take into consideration with this is maintenance cost. Annual maintenance cost, you know, some of the machines require. Laser cost, you know, lasers are good for some time, so after that they have to be replaced. Also, power supplies and other costly equipment. Also, something else that you have to take into consideration is when you're running the systems, it's not just you know, the expense of the machine. There's also a lot of consumable costs. Like I said, powder is also a consumable cost. You know, like I said, plates. You have to rakes. You know, and other consumables. Also, something that you have to take into consideration when you're looking at the system is gas. You know, some of these machines require gas to be constantly being purged to them, and that adds up pretty quickly. So another thing, like I said, another big investment is powder, right? Contemporary to popular belief, one cannot just put any any powder into an AM machine and make it work. There's a lot of science behind that. You know, there's a lot of there's morphology, you know, that you have to look at, packing density, you know, flowability. So there's a lot of variables that play a good role in getting successful solid parts. AM processes are sensitive to power properties. Like I said before, it is therefore recommended that you use powder qualified by suppliers, by machine suppliers, you know, to be able to use, at least until you have gained experience to develop process settings on your own, you know, so that's kind of important. Also, something that you have to take into consideration when you look at powders is powder recyclability, you know. Production additive manufacturing users must make a plan for how to recycle powder in an effective way. So some of the technologies, you can continue reusing the powder as long as you keep refreshing it to stay within a certain standard, you know, or chemical composition, which is very, very important to get successful parts. Something else that you have to look at is facilities. You know, as you know, here at the MDF at Oak Ridge, we have a lot of machines. We have different several, and we have a pretty big facility. So the thing you have to look at when your facility is power, you know, what are you going to use? Like I said before, gases, you know, that's very important. Also keep track of that, how much that costs. Air, you know, you're going to need clean, dry air, you know, depending on the system. And then also to run the vacuum cleaners to run into the system, you know, there's a lot of things that you have to look at. It's always very important to ask the manufacturer before you purchase, you know, what a preparation site, because that will also help. Something that you have to look at is also the machines keep getting bigger and bigger now, you know. How are you going to get it into your facility? That's really something else to look at. Like I said, also with space, you need to have controlled humidity and temperature work environment, and it also has to be very clean. And for cleanliness, you know, that's something that's very important, especially when you start looking in your facility and you think, you know, you need to plan ahead if you're going to start building with more materials, because as you could see, better to have one system that to run only one material. That's what we recommend. To have a different vacuum cleaner, to have a different breakout area, and for sure to have different tools so you won't have no cross-contamination. You know, because what happens with this when you start contaminating, getting your aluminum inside your nickel or your titanium inside your nickel, you know, that is very, very bad. As you can see here, I have some SEM pictures of some powder particles, and it's kind of hard to tell because all the powders look the same, right? But with scanning electron microscopy, if you look closely, depending if you do a backscatter or electron, different materials absorb energy different ways, so they can glow different. And you can kind of catch if there's any contamination by that just by looking at scanning electron microscopes. So here you could see around there's nickel, but the highlighted red part, that shows that's titanium. So there's a lot. You can get cross-contaminations, and when this happens, it's almost it's impossible to pretty much separate the materials, so you just have to get rid of that. And in some cases, you probably have $50,000 worth of material, and you put just a little bit of another material, you completely contaminate it, and that there's nothing you can do with that. You just have to pretty much throw it away. All right, so the other stuff to look at, is quality control. This is something that a lot of companies don't see. They just purchase systems, but then when you start trying to manufacture for somebody, you kind of already have to have a quality control system in place. Each industry has its own quality standards. Medical, you have ISO 13485, and you have to also be FDA registered. Automotive, you have ISO 9001. Aerospace, you have AS 9100. So the way I look at it, and I tell a lot of companies, it's easier to go from manufacturing to additive than from additive to manufacturing. And the reason for this is because if you're already doing manufacturing, if you're already doing supplying tier 1 or you already have this quality control system in place. And by doing that, you're already ahead of the game, because you have to have quality systems in place. Like you have to have certifications, you have to have renewals every year to make sure that you stand. But something that's nice about our industry, now I'm getting into the F42 Standard Committee. Here we actually started to look at all this. A lot of people in the industry have active ASTM standards that have already passed. Like I show here, standard specification for additive manufacturing of Type 64 with powder bed fusion. With ELI, so a lot of people are working really hard to put some of these standards together for our industry. So that way, everybody's following the same, and we're not just prototyping anymore. Pretty much, this is kind of what these are telling. So we have a lot of standards that are active, and then also a lot of people have been working really hard, currently proposing some different standards, which is pretty nice. So you have to keep an eye on all this. But then you have to start thinking, what about quality? How are you going to certify these parts, right? So there's a lot of stuff that's going on out there for that. Each company is producing a lot of different systems, with different qualification strategies, and a lot of people are looking at this, the way that currently is being done with castings and everything, sometimes using statistical control, for non-destructive testing, looking at, there's destructive testing, but that's very expensive. Non-destructive testing is also expensive. You start looking at CT, X-ray is cheaper, but it all depends on the standards. And what we're doing with the EBM technology, we have implemented for our newer systems, quality control system. And that we do like RCAM layer cam, as you can see here, which is it's a camera-based quality verification system that takes a picture after each layer, and then the image is analyzed and defect detections are, and I'll show you a little bit about that. The way that the system was implemented with the EBM system, it uses a camera, as you can see, different camera components. We use a very high resolution camera. With the Q10, I believe, is 10 megapixels. With the Q20, which is a 350 millimeter diameter by 380, we use a 29 megapixels camera. And also we have a shutter system. As you can see, some pneumatics that open and close the shutter system. And when it opens, it takes a picture, And by doing this, we have the capability to take up to 5 different pictures in a layer. We can take a picture when it's heating, after raking, after melting, so we can do a lot of different pictures. And what you see here, this is a camera picture of a reconstruction of, we were doing a lot of parts. We were doing robotic parts, qualities. and we're taking picture by picture. So from here, we can actually see and get a detailed image of what's going on within the build. So we see if there's any porosity, and then with this, we have the tools to actually quantify it. And I'll show you some of that information a little bit later. So next here, we have some examples of some other pictures that we're taking. These are actually it is a 350 millimeter image of the entire build for the Q20. As you can see with this, we have a resolution of around 80 to 100 micron pixel size. So we can detect if there's any defects in that range. The way that we do it is we can actually compare, as you can see here, we're comparing the image that was taken in the right with the actual build file. And by doing this, by overlapping them, we can actually see if there's any area that has been that has any porosity, or as you can see, any defects. We've done several testing here at Oak Ridge National Labs and also in Sweden at ARCAM, and we actually compare what we're actually looking at with CT data, and then we see how it correlates. Then here I have a video of it showing, the bottom right is actually data taken. The bottom left top is the data, and then the top right corner is the actual CT. So as you can see, if I go back to the other one, when we put this together, we actually get a really good correlation between what we see and what we don't see. Also, something else that we're doing is we're creating what we call, we can create a report from all these data images. As you can see here, there's a process we're doing, a verification build from one image. This is the data that we get. We take pictures of it. Right, we import all the data that we got from the build in our defect detector software. And then our defect detector software creates what we call layer cam report. And this layer cam report gives you the defect size and actually where it was in the part. It also has the capability to separate the different builds, as you can see here. So defect size detection was number 11. So as you can see, all the different were named. All different tensile bars. And then we can see from all the different tensile bars that we got that were numbered, number 11 was the one with the lowest density. And then we do mechanical testing, and we figure out the number 11 is the one that gave us the lowest percent elongation. So we can see by doing this stuff like this, we can see where's the density, what C height the density is, and all that, But something else that's been worked at also at Oak Ridge National Labs is we're doing automated in situ defect detection systems. So this is software that should be, we're still working on it. It should be public within probably next year. And we actually get all the data from the system, right? We run it through a different algorithm. We can detect the compare like we do before. We compare the actual build file and what we should be build file, and we can start seeing porosity. And then by doing this, we have different edge analysis tools, to try and get the best this data possible. As you can see here, we can do edge detection, different little algorithms. And then from here, we can actually start implementing the 3D model. As you guys see, these are actually some builds that we did. And then you can actually see the part rotating. And then you can see the green area, you see some of the defects that were found. You can get a better view of the system here. And you can see this is just looking inside, layer by layer, going through the data, the imaging system. And it'll tell you exactly where the defects are. Another big advantage about this technology, is that also you can do with the camera, you can do automatic beam alignment. So for calibration and everything that you do in the system, you start taking away the person, or the human contact to it. So whenever it calibrates, it'll be more repeatable and better, and you can do this with the beam, and the camera. So the way that it goes, you can focus on to get the perfect beam diameter. Like I said, I haven't said, but with the new Q systems, you start getting 100 micron beam diameter, which is a lot better than what we had before, and you start getting a lot better parts, better surface finish. So now the other thing that you can look at is once you have the build, once you qualified it, it's out of the machine, what are you going to do with it, right? So different processes require different post-treatings, right? If you take the part out of a laser system, the first thing you have to do before you cut and everything, you're going to have to stress relieve it, or stress treatment to stress relieve it, and then you have to cut it off from the plate using wire EDM or saw. So you're going to have to start planning to purchase. You have to start thinking not just of the machine, but other equipment that you're going to need for it. Like for support removal, you're going to, and also part finishing. A lot of companies do a lot. They've been very successful with tumbling, bead blasting, and also CNC machining. That different technology that you need to get the correct part, diameter, and tolerance. So in conclusions, the thing that you have to really think about it before you start purchasing a system, you have to think about safety first, and that's something very important, especially for the future of your company and the people that you work with. Also, metals AM is here to stay. As you see, a lot of companies are already going into production with it. They're flying. They've been flying for a long time. And also they've been implanted since, EBM has been implanted since 1997 when they first got their first European, ISO certification. It also requires large investment and resources, as you see that, the machines are expensive, but they can produce really nice parts, as you see this one over here on the side. Metals AM has a steep learning curve, It's always very important if you're going to do this to try and hire somebody that has already experience. But the problem with that is that there's not a lot of people out there with a lot of experience with laser EBM for production, so they're very scarce. And then also AM Metals provides the feasibility to build complex parts, and stuff that can't be built with traditional methods. So that's very, very important. Also to start thinking ahead, to start redesigning. Like I said before, we have to design for additive now, and it's not just parts, but also eventually we're going to have to start getting rid of some of the older alloys, Inconels, different titaniums, and we're going to have to start designing for additive manufacturing so you can get better mechanical properties just out of the system. All right, so with that, I'd like to thank you guys, and if you guys have any questions, I'd be happy to answer anything I can. All right?
Thank you, Francisco, for that informative session. As Francisco has shown, metal 3D printing is an increasingly important part of additive manufacturing. And as he said, we're going to try and answer a few questions now. First question, is there any new development in reducing the cost or increasing the quality of the powders?
Yes, so there's a lot of new companies coming out that are trying to do different powder techniques, to lower the cost and to improve quality. So there is a lot of new companies out there, and they're developing new methods, that are still now not good enough for additive manufacturing, but I think eventually they will be, and they'll be used for manufacturing for additive.
Where can you find more details about powder handling guidelines?
More details on powder handling. So like I said before, at Oak Ridge here, we have some people that are very involved in additive. So if you have any information, I can probably pass it along. If you need any information, I can probably pass it along, and they'll be able to help you. But also, if you ask, you have to ask the machine manufacturers. They should also be able to provide you with very good information on that.
Okay. Another question: can you describe the quality inspection a bit more? This seems like it will be a hurdle for this technology because no one really knows what to look for. Is there any work being done to understand what type of defects are detrimental for the parts?
Correct. So here at Oak Ridge, we are doing a lot of that. We're looking at what kind of defects affect fatigue, different types of mechanical properties. Surface finish, that's also something that we're working very close, looking at. So there is a lot of groups out there doing some research and publishing a lot on this. So that would help. And also the key for us, when we're developing these technologies and these inspection technologies is to try and reduce the number of defects that we find. And by doing that, we modify scanning strategies, post-treating strategies. So there's a lot of stuff that can be done to fix that.
Okay. A related question: what is the best surface finish that can be obtained directly from the machines?
So depending, laser systems have better surface finish, but EBM, there's different, the newer systems are getting really good, really close to laser. So it's kind of a hard question, depending on the material that has to do with it. Also the layer thickness that you're cutting, or that you're building with.
Okay. All right, here's another one. Are there industry-accepted standards for AM substitutions for traditional methods, or does each AM manufacturer have such substitution standards?
I don't think the AM manufacturers, have those standards. I think where it comes from is actually from the Boeings, from the GEs, that they're working with their engineers to try and find different substitution or different parts. And it's not just to replace a part. That's not really cost effective. The way to do it is to replace a part but improve it, make it lighter, make it better, with additive. That's what's going to set additive metals apart from traditional manufacturing.
Well, the GE case with the fuel nozzle, of course, that's a case where it's, one part replaces 20.
Correct.
Yeah. Here's another question.
Exactly.
What do you see as the potential or future of wire-fed AM?
Wire-fed AM, it has its, in repair, in large scale, it has its niche for sure. So I think the industry is big enough that a lot of companies are going to have their niche. So for sure it'll survive and it'll probably thrive, with big parts that cannot be built in additive manufacture, in powder bed.
Okay. Another question. What are the advancements in hybrid machines that can print and traditionally machine the parts in the same machine?
So there's a lot of companies starting to push that out there, But in the beginning there was a lot more noise, and now it's starting to settle down. I haven't really heard much about it. I do see a lot of challenges with that because especially if you're using coolant or using stuff that you can really contaminate the part before or after you deposit new material. I think it's hard, but it'll also find its niche.
How many years down the road do you think it will be for small businesses to be able to use 3D printing for standard carbon steel and at a reasonable investment cost?
Well, currently the machines, like I said before, are still expensive. They haven't really, I don't know if they'll go down in price, because a lot of companies are investing heavily, a lot of their earnings or their profits, in research. So I think it's still probably a couple of years for sure or more. It's a hard question, to look at this. I know that a lot of companies look at tool steels, look at stainlesses, and those are cheaper powders.
Okay. How does the strength of a metal AM part compare to that of machine parts of the same material?
This, I guess, depends on the material. For titanium with the EBM process, it's pretty much it's almost the same or sometimes a little bit better depending on the microstructure that you're getting. So it depends also a lot on the post-treating. It's not just it comes out of the machine and you use it. You might have to do some for nickel-based superalloys for sure. You'll have to do some heat treating to make it better or equal. And that might include also hipping to reduce some of the porosity that might be there.
Okay. Are there globally accepted properties and design allowables, or are some companies, such as GE, creating and working to their own?
So what's kind of sad is, so there a lot of companies, especially the big EOM, they're developing their own design allowables, but they're all keeping them internal, so there's not a lot of material sharing. And now with America Makes and all that, that's starting to change. They're trying to give this to the masses, and which is kind of important because then that way more companies that don't have the millions, to create design allowables will start using that. So I think hopefully it'll get better for smaller and large, medium and smaller companies for sure, and they'll be able to design for this. And also the F-42, they are developing some minimum requirements for different technologies. So that's also very important.
Beg pardon. Sorry about that. Here's a related question. You mentioned the need to design alloys specifically for AM. How do or will alloys designed for AM differ from those designed for casting or traditional metal forming?
So if you start looking at different Inconels, or different aluminum, there were the majority of the stuff, some of the stuff out there was designed for castings. You try and get the best material properties just out of casting, Or also all the hipping and some of the standard heat treatment was all designed for castings or forgings. But eventually we're going to have to redesign for just additive for different processes, like some with laser or EBM, because it's not a casting form that it doesn't solidify or it doesn't, there's different solidification mechanisms. Different materials can evaporate or different material, so you have to design for all that. So you might have to put more of something else, or something less of something else, so the chemistry might change.
Okay.
So it's pretty complex.
Yeah, absolutely. Here's another question. I was under the impression that since we would no longer be bending or forming metal into shapes and just printing a final shape, doesn't that eliminate the need to do stress relieving?
No, that doesn't make a lot of sense. By stress relieving, what I'm talking about is when you're building with let's say with a laser system, right? You currently build around room temperature. So what happens? You're rapidly solidifying a lot of little welds, pretty much. Let's say to keep it solidified. So what happens, because you're getting a lot of this shrinkage, a lot of this rapid solidification, you're starting to create a lot of internal stresses. And that's why you have to stress relieve, to be able to release all that stress that's, and by doing that, then you won't get a part that will deform over time. Because if you leave it in a table and it's still stress relieved, it'll start, it can start breaking supports, it'll start doing a lot of different stuff. So that's why you need to stress relieve the part.
Okay. Here's the last question we have time for. What is the largest build platform currently available?
So for EBM, I know for sure we have a 350 by 350 by 380 millimeter build platform. In laser system, I think it might be 400 by 200 by, I'm not too aware, sorry about that. But you can look at it, it's pretty easy. Concept Laser, I believe, has it.
Well, that's all the time we have for questions. If you still have questions, feel free to email me directly at bkoenig@sme.org, bkoenig@sme.org. We encourage you to stop by our website, advancedmanufacturing.org. Our parent organization, SME, has been involved with additive manufacturing for decades. For example, SME's Rapid Technologies and Additive Manufacturing community has been serving and supporting the technology for 25 years. Also wanted to give you a quick reminder, SME's South Tech Show runs October 27 to 29. That's at Charlotte, North Carolina. And the Fab Tech Show is November 9th through 11th in Chicago. Thanks for joining us for this Additive Manufacturing Media webinar. We hope you found it informative.